Okay, the recording has started. Welcome everybody for on the second day for the Winter School Industry Diagrams for Optimization. It's a big pleasure to see you all. Now, also, I would like to just introduce you Quentin Cappart to give our next talk. Quentin, in many people's world, is one of the stars nowadays that is mixing reinforcement learning with optimization, with dynamic programming. So it's really a pleasure to know that he's also working with a lot of things related to decision diagrams. So he's now an assistant professor in artificial intelligence in the Department of Computer and Software Engineering at Polytechnique, Montreal, very closer to Toronto, very good friends. He got a PhD in 2017 at University Catholic de Leuven, and then he joined as a postdoctoral fellow CIROT from 2018 to 2020, where he's now also assistant professor. So Quentin, go for it. We're excited for it.
Thank you very much for the introduction, and hello everyone. Thank you for inviting me to give my talk. I'd like to present my work, so thank you very much for this opportunity. So if you have questions, first, don't hesitate to interrupt me. I prefer to skip a few results, and I want the session to be interactive, so don't hesitate to interrupt me. So today I will speak about how we can learn optimization bound, and for that I will propose a method based on decision diagram and reinforcement learning. But before moving to the content, I would like to give you some sense of why I decided to move to this research field. And the reason is quite simple. I love solving puzzle games. When I was a kid, I spent many times to play computer game, like a puzzle game, to solve some problem. I don't know if you know this one, the Incredible Machine. So we have a mission here. The mission here is to take the cat and put it here into the basket. And here we have few items that we can use. So I like to solve this kind of puzzle. So now what changed? Actually, it is still my daily hobby. I still love to solve a problem, puzzle game, but now I call them combinatorial problem. So I'm still playing computer game like Baba Is You. I don't know if you know him, but it's very challenging. But I also solve problems that are useful for the industry, like in a railway system, in transportation, or schedule management. So my research interest is to solve combinatorial problem and to design new methods for that. And one method that I like very much is the combination of search, like a branch and bound, and machine learning. So combinatorial optimization, as you know, it is very difficult because we have a huge amount of possible solutions. So we have some solutions that are infeasible, some actions that are some solutions that are feasible, and some solutions that are the best one. And we want to find the best one. So interesting combinatorial problems are NP-complete or NP-hard. So we don't know any efficient algorithm to solve them exactly. So how we can solve them in practice? We have few methods for that. First, naive way is to enumerate all the solutions until the best has been found. It is what we call exhaustive search. So of course, it is very expensive because I have to swap over all my possible solutions. So it is not efficient in practice, but it has a main benefit is that we can get guarantees. And you will see during my talk that guarantees is something that I like very much. That's something that is very important. So guarantee, it means that at the end, if I can be sure that the solution that I have found is the best one because I have explored everything. So at the other extreme, I can use a kind of intuition to build my solution. So I use my intuition, and maybe my intuition will give me this solution. Okay, that's what we call heuristic solving. It is very cheap, but I have no guarantees. I do not know that this solution is the best one or not. And even if I am able to construct this solution, I do not have any proof that this one is the best one. So I have no guarantees. So what we can do is to try a mix between both ideas. Enumerate solution in a clever way. That's what we call search-based method. And depending on the trade-off on when you want to rely on heuristic or on the exhaustive search, you have different methods. You have incomplete method like local search or meta-heuristic, where you have a high dependency to the heuristic. And you also have constraint programming and integer programming, where you have a complete search and you use also heuristic. So that's the different method to solve combinatorial problems. So how to formalize constraint optimization problems? So you need decision variable, domain, constraint, and objective. And I will use a running example, the maximal independent set. So that's very good, Andre and David, that you spoke about it yesterday. So I don't have to explain it. So we want to select the set of adjacent varieties, of non-adjacent varieties with the maximum weight. So I don't go into the detail about the mathematical model, but the thing that is the most important is that we have a variable, a binary variable that is attached to each variety. do I want to select this vertex in my set or not? So that's the maximum independence. I can represent the solving process by a search. And this tree, I will expand all the possible variable value assignation. So at the root node, I have two possibilities. Let's say I take my variable x1. I can decide to not select it or to select it. So I move to another node, and then I have two decisions for the next variable. I don't select it or I select it. And I do it for all my variables, x3, x4, and x5. And at the end, all the leaves of my tree are possible solutions. Some of them are non-feasible, some of them are feasible, and one of them is the best one. If I take this leaf, for instance, it means that I select x1, okay, x1 is selected. I don't select x2, I don't select x3, I select x4, and I don't select x5. So that's my solution with a wave of 5. It's not the best one. I can find another one which is better with a wave of 11. So the question here is, how can I explore this tree? We have complete search method. The idea is to explore the tree in order to find the best solution. And ideally, we want to prove that the solution obtained is the best. It means that we want to complete the search. In some extent, it means that I have to consider everything here in some extent in order to be sure that I have the guarantee, okay, my solution here is the best one. How can I do that efficiently? Generally speaking, the algorithms are based on two components. We want to decide how the search is directed. It is a branching. So do I prefer to go in this direction or this direction? And also the pruning. I want to prune, to remove some part of the tree that are not useful, where I am sure that I don't contain the optimal solution or solutions that are better than the one that I have currently have. So it means that, okay, maybe I can decide to skip this part of the tree. I don't want to explore them because I can obtain few information that tell me, okay, I am sure that this part of the tree is useless. This can be done by propagation, that is what is done in constraint programming, or bounding, for instance, using the linear relaxation in integer programming. And so using both components here, we have a very famous algorithm, which is branching bound. It is a kind of generic framework to explore the tree, and it is based on two ingredients. So the branching, selecting the branch to extend first, and also the bounding, computing bound on the objective function, both primal and dual, and use it to compute to prune the tree. And we have many solving methods that are based on some extent to branch and bound. They only differ on how operations are done inside the algorithm. So for instance, in integer programming, we have a generic way to obtain dual bound using the linear relaxation. In constraint programming, we don't have a generic way to obtain dual bound, but we are very flexible on how the branching is done. That's why both methods here have strengths and also weaknesses. But what is important is that both branching and bounding have a key importance in the efficiency of the solving procedure. So the challenge here is that actually finding the best branching and bounding strategy is something that is very hard, because we have many strategies that are possible, and also it depends on the specific problem. Maybe you will branch in the same way for a problem, but for another problem, it will be another way if you want to be efficient. And also something important is that there is a kind of trade-off between computation time and accuracy. Sometimes you will spend a lot of time to compute a very good branching, but it is not worth it because you will pay too much time to compute your branching. Maybe you know about a strong branching in integer programming. This idea. It can be very expensive, and sometimes the price that you pay to compute the branching is not worth it. And finding the best branching on bounding strategy is sometimes a lot of time very hard. So what we can do? And for that, we can decide to move to another world, and I will go back to the heuristic solving, using a kind of intuition to build my solution. We have two ways to doing that. The traditional way is to use an uncraft heuristic. As a user, as a developer, I will manually design my heuristic for solving the problem. It can be very simple, like for the maximum independence set, my heuristic can be, I will select the variable with the highest width, the available variable. So this one, because I want to maximize, it makes sense to select first x5 because I have a width of 7. And now I cannot select x4. Okay, and the second one, I will take x2. I cannot take x1 and x3. So, okay, I have my solution with a width of 11. So here it's quite easy to do it, but because my heuristic is quite simple. Generally speaking, when we want to be efficient, we need to think about the structure of the problem. We need a good understanding about the problem. And also the heuristic must be designed specifically for each problem, which can be time consuming, especially for end users who are not so familiar about the solving method. That's why we have now another trend to build heuristic is using machine learning. We train a model to learn a heuristic. So we use past experiment or historical data to learn the heuristic that we will use to solve the problem. It's an idea that is actually quite old, but with the popularity of deep learning, now we'll see a lot of work from that. So the approach is quite generic, and also for the user, it reduces the burden of understanding the structure of the problem. So we can do that in different ways. First way is what we call end-to-end learning. The problem is directly solved using machine learning. So we have the definition of the problem, and I have a machine learning model that I can use directly to output my solution. So it is a picture that is taken from the survey of Yoshua Benjo, André Lodi, and Antoine Provost. And so for my maximum independence set, it's quite simple to visualize. I use training data, I build a model, I give to my model an input of my problem, and my model gives me a solution. For instance, this one. Okay, I have my solution. So I have a few limitations with end-to-end learning. And I don't speak about the fact that training a machine learning model for solving combinatorial problem is very difficult, and we need a lot of data and computation time. But we have another limitation that is more conceptual. The goal of machine learning is to predict an output. And even if the predictions are very, very accurate, machine learning can do some mistake because we are doing prediction. And by its own nature, machine learning will do mistake. Even if I take one of the simplest tasks, which is very, very studied in machine learning, which is the digit recognition for the MNIST datasets, the best accuracy that is reported in the literature is around 99%. So it is a very good accuracy. The models are very good, but we do mistake. And the fact that we will do mistake is a real issue for combinatorial optimization. I don't want to obtain solutions that are infeasible in practice. It means that in some sense, my model can output me a solution that will predict me this solution with conflict in my variable. And that's something I don't want to have. I want to have guarantees here. So that's why, personally, I don't like so much the using end-to-end learning for solving combinatorial optimization problem because we need guarantees. And so another option that we can do is to combine learning and searching. So it's like taking the best of the two worlds. I will use branch and bound to obtain guarantees and drive the search, but it is quite difficult to use because I need to know how to branch and how to bound. And I will use end-to-end learning. And so here it is the problem that we have no guarantee, but it is easier to use. So the idea is to use machine learning to speed up branch and bound. So the duty, the job of both of them is different. The job of branch and bound is indeed to solve the problem, so we can obtain the guarantees. And the job here of machine learning is not to solve the problem, but only to help branch and bound to take better decisions. So during the search, I will call machine learning to help my branch and bound to take better decisions. So the job of branch and bound is to solve the solution and to prove optimality. And the goal of learning is to only speed up the search. So it's not a problem if my machine learning will do some mistake. It's only used to speed up the search. Okay? So the question is how we can do that in practice, how I can learn something in branch and bound. And actually, it is my main research topic. If we look the word branch and bound, we have two important concepts, branch and bound. And it gives us two options that we can leverage. First option is learning to branch. I can use machine learning to guide the search inside the tree. That's the branching part. And if you look into the literature, you will see a lot of work on this topic. So most of the work are published in the NeurIPS or TPI or also CPIOR. And we have a joint work with André, where we propose a method that is based on reinforcement learning and constraint programming to guide the search. So I think it's a promising direction. But today I want to speak about the other option, learning to bound. Here the idea is to use machine learning to obtain bounds for pruning the tree. And what is very surprising here is that actually in the literature, there's almost no work on this topic. A lot of work are done on branching, but not a lot of work are done on bounding. And the reason is that it is a difficult task. And why it is a difficult task? First reason is that we need guarantees. As I told you previously, machine learning can do some mistake. And we don't want to do mistake when we compute bound. Why? Because the bound are used to prune some part of the tree. And I don't want my bound to be wrong. If I have a bound that is wrong, for instance, if I compute an upper bound that is lower than the objective function value, it means that I will maybe prune my optimal solution. And that's something I don't want. I don't want to compute the wrong bound, so I need guarantees. So that's why conceptually machine learning may be not very efficient to compute bounds. So example, if I compute an upper bound that is lower than the optimal solution when I want to maximize. And the second reason is that the common bounds that we use are inflexible. If I take integral programming, the common way is to use the linear relaxation. So I have my formulation and I will relax the integrity constraint. So, okay, I obtain my linear relaxation bound. But the problem is that the bound is inflexible. It means that, okay, I have my bound, but I cannot improve it. Each time I compute my linear relaxation for my problem, I have the same bound. So I have no really option here to learn something. Maybe I can try to learn to do a linear relaxation faster, but I don't think it will be a big deal. So it is not so much to learn here. So what can we do now? So thanks to David and Andre yesterday, you know that decision diagram can also be used to obtain bounds. We can obtain computation optimization. Using relaxed DD, we can obtain dual bound that can replace the linear relaxation. And using restricted DD, we can obtain primal bound. We can replace heuristic solution. And something that is very important here, and it is the key of this presentation, is that the bound that we are obtaining are flexible. As a user, I can change the quality of the bound if I make the good decision when I build my decision diagram. I can play on the maximum width. So if I allow a larger width, I can get better bound. I can also play how the nodes are merged for the relaxation or deletion for the restriction, and also on the variable ordering. In practice, playing on the node merging and the variable ordering are something very, very difficult. We don't know how to do it efficiently. But we have an opportunity here. I can use machine learning to drive the compilation of DD in order to obtain tight bounds. And in practice, that's what we did. We play on the variable ordering. We use machine learning to obtain a good variable ordering for compiling DD. And using that, we can obtain good optimization bound, both primal and dual. So the topic of this talk, I will show you how you can learn optimization bound using reinforcement learning. And we see that the bound that we learn can be useful in branching bound. We can reduce the size of the search tree. And we'll analyze the speedup that we can obtain. And also we have some challenge that we have to tackle. I will speak about that. So basically, the content of this talk is available in the 3 publications here that we done. It's a joint work with David. And when I make this list, I have to realize that maybe we should stop to use the word improving for the title of the publication, because 3 of them have the same beginning. So, okay, that's the motivation of this work. So let's go back to the maximum independence set. So for that, as you know, we need a recursive formulation, the dynamic programming model. So it is exactly the same as the one that Andre presented to you yesterday. So we have state for the node. Here, the state are the vertices that can be still inserted in the solution. So at the root node, okay, I can still use all my vertices. Everything is available. My arc, I will insert a vertex on the solution or not. And the cost is, it is the weight of the vertex, if it has been inserted or not. So for instance, if I decide to don't insert x1, if I don't insert a, no problem, I can still use x2, x3, x4, and x5. So it is my state. Now, if I decide to insert x1, I cannot choose x2 because it is adjacent, and I cannot choose x3. So I have x4 and x5. That's my state. So it is really the same as Andre explained yesterday. So I continue, I compute my DD using this mechanism. At the end, all the paths from the root to the terminal node are possible solutions. And the optimal solution is the one with the longest path, which is this one. I select X2 and I select X5. So X2 and X5, which give me a cost of 11. That's my optimal solution. The benefit is that the longest path can be computed in polynomial time, but the diagram grows exponentially with the number of variables, so you cannot compute this exact DD in practice. So this directly prevents the compilation of exact DD, and that's why we'll use relaxed and restricted DD, so the approximate DD. So in order to show you visually what is happening here, I will use this kind of visualization. So let's assume that I have my exact DD here with the optimal cost of 11. So that's my optimal solution. I don't want to compute the exact DD. So I will do an approximation. I will set a maximum width. Here, my maximum width will be 2. And I will compile the DD while taking into account this restriction. What I can do is first deleting node. I will obtain an under approximation. So I will lose a solution. So here I will delete this node. And that's my resulting DD, a restricted DD. So I lose solution, so I have another approximation, and the longest path here will give me a heuristic solution, a primary bound. So here I have a lower bound of 9. Okay. What I can do instead is of deleting, I can merge node. Here I have an overall approximation. I don't lose any solution, but I add a few solutions that are relaxation. So I have a relaxation of my problem. It's a relaxed DD. And now, when I compute the longest path, I have an upper bound. It is my dual bound. So I get my upper bound, which is 13. And then I have two bounds, 19 and 13, that I can use inside a branch and bound algorithm as the one that David spoke yesterday. Okay, can I do something better? Yes. So I can consider another variable ordering. And that's the only thing I will change. I only change the variable order. So the exact DD will be different. But at the end, if you compute the longest path, you will still obtain the optimal solution. Now, when I delete node, I obtain a restricted DD that is different. But now, the bound that I will obtain can also be different. So I can obtain other bound when I change the variable ordering. And here, in this case, I have a bound of 11, which is equal to the optimal solution. So I can reduce the gap here. I have reduced the gap drastically. And for relaxed DD, I have the same ID. I will obtain a new decision diagram, and the bound can be different of 12. And so I can also reduce the gap. So I obtain tighter bounds only when I play with the variable ordering. So the variable ordering is the order on which the variables are considered for the compilation. It defines the structure of the diagram, and it has a huge impact on the quality of the bound. So it seems to be good to obtain the best ordering, but unfortunately, it is a difficult problem. By difficult, I mean it is impaired in general. And even improving a given variable ordering is also impaired. Actually, it means that we need to find the best permutation across all the variables. And also, it is something that is difficult to model for a large variety of problems. So what does it mean to build a model to compute the best variable ordering for computing DD in general? That's something that is very difficult, so even to model. So the current methods for that are mainly based on heuristic. So I recap here a few works, one by Bergman and other one Van Hoof, which was published this year at CPIUR. So we can use one heuristic, which is the minimum number of states. I will select each time the variable that will appear in the fewest state in the layer that I am constructing. I can also use the minimum vertex degree. I will select the variable associated with the lowest degree, which is available. So that's just a greedy heuristic. I'm just looking at the next layer, what will be my best variable according to some criteria. And also, that's the last work, we can also design a portfolio approach where we have a different heuristic that we can use, and we select the best ordering among the set of the alternative. So on this work, it was not done on the graph, on the maximum independent set, but on the graph coloring. So here I will propose a method that is based on reinforcement learning. So, okay, do you have a question so far about the motivation of this work? Okay, great. So reinforcement learning. So the research idea is to use machine learning to learn an appropriate variable ordering because that's something that is difficult to solve. And we propose here a method based on reinforcement learning. Why we decided to use reinforcement learning, you will see the reason will be quite clear. Spoiler, it is because we use a recursive formulation. So reinforcement learning. So we have an agent that will interact with an environment. So the agent can do some action, and each time the agent will do an action, it will collect a reward and move to another state. So the agent do an action, it moves to another state, and it will collect a reward. And so then the agent can do another action, collect another reward, and move to another state, and so on, until the lifetime of the agent, until a terminal state has been reached. And the goal for the agent is to maximize the sum of the reward that he will collect during his lifetime. So that's the goal of the agent. So solving a reinforcement learning problem, basically, it only means that we want to select what is my action to do. So find a kind of policy for my agent. What is, if I am in this state, what will be my action? So how do we select the action to? This problem can also be represented as a tree search, a search tree. So we begin at that state 0, my initial state. I have different actions that I can do. Each action gives me a reward, I move to another state, and so on and so on. So in theory, it is quite easy to solve this problem. What I can do is I can compute an estimation of the quality of each action. It is what we call the Q value. For instance, my estimation here for my Q value is 3, and my estimation for this action is 6. What is important when I compute the Q value is that it is a function not only of my next reward, but about all the reward that I can collect if I do this action. So it is a kind of estimation of really the quality of each action in the long term. And so when I have the Q value, I can take the action that has the best Q value. That's the greedy policy. And a nice result is that when the Q values are exact, so if I am able to compute them exactly, the greedy policy is optimal. So we only select the best Q value, and if the Q value are optimal, I am sure that I will converge, I will find the best solution. Okay. In practice, as you may assume, we have a lot of problems, and this cannot be done because computing the exact Q value requires to explore the whole tree. So if I want to compute the exact Q value here, I need to have information about everything that will happen here, which is not possible in practice. So because the search space is too large, so one solution is to use an algorithm like a Q-learning, where we begin with few value for the Q value, and we iteratively improve it using incomplete information. So we improve the step by step the estimation of the Q value. And the other problem is that when we use this algorithm, we need Q value for each pair of action state. So for each state action pair, I need to have a Q value. So I need a Q value here, 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 here. And because we have an exponential number of states, we have too many Q value to compute, and it's too large to fit into the memory. So the idea here is to use deep Q-learning, that's one algorithm, where the idea is to approximate similar state and action using an neural network. So the rough idea is to say, okay, if my state 1 is similar as my state 2, and this is approximated using a neural network, and if I do action 1 for state 1, I will probably do the same action for the other state. So that's the idea. The idea to approximate the Q value, the Q function using a neural network. Okay, I don't want to go into the detail about the reinforcement algorithm that is used, because in this work, we didn't change any algorithm. We use an algorithm that was already done, the deep Q-learning. So that's something that was already present in the literature. But what is really important is more the environment that we use. And the key observation that we can do is that both decision diagram and both reinforcement learning use a recursive formulation. And the recursive formulation can act as a bridge between both tools. I like very much the fact that Andre showed you yesterday that the decision diagram can be a bridge between dynamic programming and linear programming, integral programming. Now I will show you that decision diagram can be a bridge between operation research and also the machine learning world using this recursive formulation. So for the recursive formulation, we have the Bellman equation where I need to define the state, the control variable, transition function, and transition cost. In the reinforcement learning, it means that we need to define my set of states, the action that can be done, what is the impact of doing an action, and also what is the reward of an action. And this, I have to define it for my decision diagram construction. So really the idea here is to cast the decision diagram construction into a reinforcement learning problem. So that's the goal here that we want to do. And that's what I will present now. It is a generic framework to do that, a generic framework to learn optimization. So, okay, let's assume we have a combinatorial problem that we want to solve, like the maximum independent set, and I have a specific instance I want to solve. My first step is to build a recursive formulation. So the way to build a decision diagram, so it is my recursive formulation. That's really the most important part. When I have the recursive formulation, I am able to construct the restricted DD. When I have my restricted DD, I can obtain my primary bond. Okay. I can do the same for the relaxed DD. When I have my relaxed DD, I have my dual bond. The only difference is that for relaxed DD, I also need to define how the merging is done, the relaxation operator. And when I have both bonds, I can use them in branching. So that's what David spoke about yesterday, using decision diagram in branching. Now let's use machine learning. From the same combinatorial problem, I will generate training instance, either using a random generator or historical data. So here I assume I have an instance generator. And so for the same recursive formulation as previously, I will build directly my reinforcement learning agent. And using the training instance, I will train two neural networks. So this one, the first one, is dedicated to predict what is the next variable in my relaxed DD. So I use this to compile my relaxed DD by obtaining a new variable order, my next variable to insert into the DD. And I have a second neural network that do the same job, but for restricted DD. And now I have closed the loop. Using the recursive formulation, I can build bond, and I can use machine learning to obtain better bonds. So the link is done really thanks to the recursive formulation. Now, in my presentation, I will move to the different steps of this process. But before that, everything is clear so far? Okay, great. When I ask a question, also, it gives me the opportunity to drink a little bit, so that's good. So, okay, what is the recursive formulation? So the recursive formulation is really the environment that we use for compiling DD. I need to define my state. The state is the information about the instance to solve. So I have information about my instance. So for the maximum independent set, I have my graph, okay? I have wave from my different node. And also I have information to tell me, okay, this node has already been inserted into the D or not. Also, I have the sequence of variable already inserted into the my DD. And I have the DD that is partially constructed. So for instance, okay, that's my partial DD that is already built using only X1 for the maximum independence. So that's an example of one state. My action and my transition is that I will select a new available variable. For instance, I can select variable X2. So that's my variable I will select. And the transition is really, I will use my construction rule of the DD to build the next layer. So, okay, that's my new state. And it is my new state where I have my DD, which has now the layer 2. Okay. Now, what is really important, it is the reward function. How do we define a reward here? How do we compute the DD in order to try to obtain the better bond as possible? So the goal is to obtain the tightest bond as possible. And so the idea, the intuition behind the idea is that when I have an upper bound on my objective value, I want the upper bound to be as low as possible. And when I have a lower bound, so the primary bound, I want the lower bound to be as high as possible. So I want the bond to be tight. So for the dual bond, it's very low. And for the primary bond, it must be high. That's what we want. So when how do we do that? we compute the reward by computing the increase that we have in the longest path when we add the new layer. So it will be very clear with a small example. So it is my current state. At this step, my longest path is 3. So that's my current longest path before the insertion of my next variable. I insert my new variable. So my longest path now is 4. It's my longest path. So my longest path after the insertion is 4. That's my current longest path. So my increase is 1. So I have increased my longest path of 1. So now, if I want to build a relaxed DD, because I want my bond to be as slow as possible, I will penalize the increase. So my reward for the relaxed DD is really a penalty. It's -1. I penalize the increase of 1 when I build the relaxed DD because I want my upper bound to be as slow as possible. And for the restricted diagram, it is the opposite. Now it is really a reward. I want my lower bound to be as high as possible. So now I have a reward of 1. So if I was able to obtain an increase of 5, it will be better for the restricted DD, but worse for the relaxed DD. Okay, and it gives you also some sense of why we need to build a separate model for restriction and relaxation. Okay, so the main question now is how do we select the next variable? So it means that we need to define the structure of the neural network here. So the training algorithm, it's really Q learning. The goal is to learn a Q function that gives me a Q value for each state action pair. So I want to build this function here and to parameterize it. So for that, I use a standard deep Q learning in the literature. I use the same as Elias Kalim in this publication. So I won't speak about it because it is really the same, but the idea is to use a standard reinforcement learning. You can use any reinforcement learning that is existing. And for the training, we generate random instances. So what is interesting also is the neural network architecture. So it means that we need to embed a state as input of a neural network. How we can do that? So that's the input of my neural network, my state and my action. So first, I need to represent my state in a meaningful way for a neural network. And for that, I represent it as a graph for the maximum independent set. So I will use the graph structure. That's the structure I will use for my instance. So I have my graph, so the relationship between the node and the edges and the connection, and I will add feature to each node. For instance, I will add the true feature, I will add the weight of the node, and the fact it is a binary information if the node has already been selected or not inside my D. So that's my representation. And in deep learning, we have an architecture that is very, very suited for this kind of graph structure. It is what we call graph neural network. So the idea is to use a graph neural network. So if you don't know how does it work, it is a rough idea. We have a graph as input, and we will use this kind of architecture to transform or to embed the graph into a vector of feature. So it really transforms this graph into a vector of feature that is meaningful, that represents the graph in a meaningful way. How does it work in practice? It's really like a convolution for images. So when you want to train something using image, you have a grid of pixels like this one, and you do convolution. So if you want to predict something for here, you will take information from the neighboring pixel. For the graph, it is the same idea, but instead of using convolution with pixel, you will use information from the neighboring node. So to compute kind of representation for this node, you will use information from him, and from him, and you will use several layers to obtain more complex representation. So at the end, from the graph, you use convolution and you obtain a representation as feature. Okay, so I have a vector of feature that represents my graph. Now I will add prediction layer. So it is a simple, purely connected neural network that at the end computes the Q value. So, okay, I train a neural network that gives me the Q value for my state and my current action. And when I have trained that, my next variable selection, I compute the Q value for each of my variable, okay? And I will select the one with the highest Q value. So that's my greedy policy. So that's the idea of how do I select the next value. And the key is to train the neural network using this process. Using the training algorithm, and the representation that is presented here. Okay, now let's have an example of the diagram is constructed. So at the beginning, so we begin to look here, we have no variable inside my state. Okay, oh, maybe a question here before I move to that. So about the neural network, instead of vector, we have graph representation. Is the convolution fast? Is vector is used a matrix multiplication so very efficient? Actually, it is a point I will discuss after. It is not so efficient and we have some trouble in terms of efficiency. I will show you some experimental results, but indeed, it can be not efficient. Okay, and we can talk a little bit after. Okay, so we have a state with no variable at the beginning. So my current environment is this one. So I use my neural network to obtain the Q value for each variable. So, okay, and I will select the variable with the highest Q value. So in this case, it is x2. So I use x2 for constructing my next layer. Okay, so what is the change into my longest path? At the beginning, before the insertion, my longest path is 0 because I have only the root. And now my longest path is 4, this path. So because I am building the relaxed DD, I want to penalize the increase. So I have a reward of -4. Okay, and here my action indeed is inserting x2 because that's the one with the highest Q. Okay, I am in my next state. In my current state, x2, okay, I have my environment that has a change. So I am here. I cannot use x2 anymore, so it is not available. I recompute the Q value. So now I select the one with the highest Q value, it is x3. So that's my action, inserting x3, and I build my next layer. What is the increase on the longest path? Before the insertion, it was 4. After the insertion, it is still 4. So my reward is 0. And I continue until I reach my terminal state. And my terminal state in this case is when all the variables have been inserted. Okay, so that's how you can construct relaxed decision diagram using reinforcement learning to obtain your variable order. Okay, few questions?
There's a comment from Rahul.
Yes, so you mentioned that the state includes the partially constructed BDD, but the neural network doesn't take into account the partially constructed BDD. So we are keeping about, okay. So indeed, in my state, I use the current BDD, but the BDD is not used as input of the neural network. So we use it for keeping in track the construction, but it is not used as input of the neural network because we observe that it is not, I won't say it is not useful, but it is not required. It might be another option, that's something we want to do in future work, is to use only the BDD representation as the input of the neural network. What is nice with this idea is that we can be generic for any kind of problem. In our case, so far, we are depending on the specific problem because we represent the maximum independent set instance as the input. But if we are able to only use the DD representation as input, we are generic to any kind of DD construction. Does it answer your question? Okay, great, thank you. So now, one question that you may ask is how good are the bonds that we obtain? And so I will present now few experimental results. So for the training configuration, we'll generate dataset from 90 to 100, graph of 90 to 100 nodes with different levels of sparseness. We have 4 levels of sparseness, and we generate Barabasi-Albert graph. For the diagram width, we consider for the training width of 2 for the relaxed and the restricted DD. For the type, we build a separate model for relaxed and restricted DD because we observe in a few experimentation that you cannot use, you can, but it's not efficient. So it's not efficient to use a relaxed DD to compute variable ordering for restricted DD. So that's not efficient. So that's why we build a separate model. And for the training time, we just set a maximum of 20 hours of computation on GP. So for the evaluation, we generate 100 other graphs from the same distribution. So it means that the same number of nodes between 90 and 100 and the same level of sparseness. So we have 4 different models, 1 per level of sparseness. The width for the relaxed DD that we use is 100 nodes for the evaluation. And why we did that and not 2 is because we want to show that the approach that we have is robust when we increase the size of the DD. And for the width for the restricted DD, it's only 2 nodes because the bonds that we obtain are actually already very good. And the metric, we compute the optimality gap and also the execution time in few experiments. And for the baseline, I won't explain it into the detail, but I will compute also the linear relaxation when I compare relaxation, and also 2 heuristics for computing the variable ordering. So mean in state, mean here is the one that is commonly used. And also, just to be sure that I'm not learning something random, I will also compare with the best of 100 random ordering, the best one. So, okay, that's experiment for the restricted DD when we want to learn the primal bond. So the graph here are performance profile. So basically, the upper is the curve, the better is the method. And RORS, reinforcement learning, is the yellow one. So it is one, so it is one. How to read this plot? So it means if I take this position in the graph, it means that for 100% of the instance, I have an optimality gap which is less than 10%. So that's how you read it. And basically, the upper is the curve, the better is the method. So the blue one is the random one. So this one is the average of random. And the shaded area here, it is the best of the 100 random. So we can see that for graphs that are very sparse, the reinforcement learning does a pretty well job. We can compute the best bond. The bonds are very tight. And we observe the same trend when we increase the density of the graph. So even for dense graph, we observe the same trend. So the model here computes better primal bond than the other baseline related to D. So that's something good, but actually that's not the best result, but because primal bond, you can obtain it using other heuristics that are not related to decision diagram. What is much more interesting is to see how does it perform for computing dual bond, because we have less alternative here. We have the linear relaxation, we have DD, but it's much more difficult to obtain good linear both dual bond. So now I add the linear relaxation bond here in purple into my comparison. So for graphs that are very sparse, so it is quite easy to solve, the linear relaxation here is 100% for almost every graph. So we have an optimality gap of almost 0% for almost all the instances, but reinforcement learning here using our variable ordering is able to do the same job. If I take another ordering, so the mean state, we don't have this result. Now, when I increase the density of the graph, it is much more difficult to solve. So the linear relaxation here is the best one. Okay, it is the purple one here. And the best method among the ordering in DD is the reinforcement learning. But it is not better than the linear relaxation. When I increase the density, the linear relaxation begins to struggle. And the trend is more severe for the graphs that are very dense. And in this case, the ordering that we learn is able to compute the tightest bond. So the model computes better dual bond than the other variable ordering. And also when we have dense graph, we are better than the linear relaxation. So that's not over. And now I will move to my favorite slide. I want to go to analyze more this situation because it is a situation where the linear relaxation is better. So what can we do? Actually, that's where the magic of DD came into the game, is that the linear relaxation bond is inflexible. So, okay, I am better with the linear relaxation, but I cannot improve it. But with decision diagram, I can improve it. I am flexible, and I can do it very, very easily. I can just increase the width of the DD, and I can obtain better bond. That's what we did, and we have result here. So when I consider a width of 100, so it is the same situation as here, but presented using a bar plot. The linear relaxation gives me an optimality gap in average of around 2.5%. The best method for the ordering is the reinforcement learning around 5%. Okay, that's the same result as here. But now when I increase the width of the DD, I can obtain better bond. Using a width of 1000, I have a bond that is roughly equal to the linear relaxation. But I can still improve it. I can go to a width of 10,000, and now I am very close to the optimal solution. and the linear relaxation still have the same value. And what is interesting is that if I take the second method for the variable ordering of DD, the meaning state, it is still worth using a width of 10,000 than the linear relaxation. So it means that we can learn something meaningful of the board. And also, the model that I use here is still trained using the D of size 2. So it means that we are robust when we increase the size of the D. Okay, so now when I look in terms of execution time, the linear relaxation is by far the most efficient. So it's almost instantaneous. But if I look the other method related to DD, so we are still reasonable if I only want to compute one bond. So here I take 1.5 seconds, but when we increase the width, the less efficient is the meaning state, because we have to explore different alternatives for the value. Okay, so the same model, which is trained with diagram with a width of 2, is used. I don't need to retrain it. And the model is also robust with the width increase, and the execution time still seems to be acceptable. But when I will plug it into branch and bound, it is a different story. So now the last question for my presentation is to see how I can use this bond inside a branch and bound algorithm. So my first branch and bound algorithm, the LP relaxation use click, yes, that's we'll do comparison with Cplex, and well, in the Cplex comparison, we use the click formulation. So for the first branch and bound algorithm, it is the one that was presented by David yesterday. So roughly speaking, we have a set of nodes in the branch and bound tree, and for each node, I compute the primal bound using restricted DD, and for that I use my variable ordering using reinforcement learning. I do the same for the relaxed DD in order to compute a dual bond, and I use the bond as in regular branch and bound. So what we observe, so here I have only a comparison with our method and main heuristic. We observe that we can reduce the size of the decision diagram of the search tree. So here you have the number of nodes explored until the instance is solved. So it means here for 100% of the instance, I have less than 1 million nodes that is explored. If I want to explore to solve all the instance here for the meaning state, I need to have more than 5 million nodes, explore 5 million nodes. So the result here seems to be very, very interesting. But the problem now is that when I look the execution time, it is not the same story. We are very, very bad in terms of execution time. And the reason is that computing and the prediction by a neural network using GNN, then a fully connected the deep neural network is costly. And it is costly, and that's something I have to do a lot of time during my search. Each time I am in a node in my branch and bound, I have to compute my neural network for each variable ordering that I want to compute, and I have to do it again for each node. So it's very, very costly, and that's why it's not pay off here in terms of execution time. So the improvement on the search, so even if I can improve the search, is not enough to compensate the increase in computations cost. So that's a bad news. So what can we do? And say here, that's the last result I will present to you today. We can improve the branch and bound. And the intuition is that, okay, I will allow my variable ordering to be slightly less accurate, but more efficient time-wise. So we bring some modification inside the branch and bound algorithm. So that's the improved version. So first, when I compute the primal bound, I will use the heuristic ordering. So I don't use my method based on reinforcement learning and the neural network. So it is based on the observation that the primal bound have an impact that is almost negligible on the tree. So the dual bond is much more important. So we only use the learning ordering for the dual bond. So for the dual bond, I still use my variable ordering using reinforcement learning, but instead of predicting the next variable each time, I will predict the M next variable. So I will, in a single shot, predict few variables in the same time. So it spares me a lot of call of the neural network. It is under the assumption that we can predict several variables in a single shot without updating the state. So it is an assumption we lose accuracy, but we gain in terms of performance, in terms of execution time. And we use the bonds as usual. And also, the last modification is that we use the ordering only for the first k node of the branch and branch tree. So it is under the assumption that at the beginning of the tree, it's very important to have good bond. But when you are below in the tree, it's less important to have good bond. You can rely on bonds that are not so good. But it is really at the beginning of the search that it's important to have good bonds. So we use the learning ordering only at the beginning of the search. Okay? And so the modification here gives us a model that is slightly less accurate, but hopefully more efficient time-wise. So experiment that we did here is that we use the learn ordering only for computing the dual bond. The model is called only for the first 50 nodes of the branch and branch tree. And also the model predicts the next 5 variables each time. So each time I compute a variable, I will predict the next 5 variables. That's the result that we have. So as we expected, we are slightly less accurate. The bonds are less tight, but in terms of execution time, we can beat now mean state. We are better. Okay, so we lose a little bit on accuracy, but we gain a lot on the execution time. Okay, so that's one message that I wanted to put here. We can compute something that is very powerful, but we have to take into account the execution time to compute this model. Okay, so now last slide of content. So how does it compare with Cplex? So for that, we use graphs that are more challenging to solve. So we compute, for the training data, we consider graph of a Erdős-Rényi model as the one as David presented yesterday of around 250 vertices. And for the test, we use the same model and we do comparison on graph of 200 vertices, 250, and 300 vertices, using the same density as the one for the tree. And for the Cplex, I use a Cplex that is based on linear relaxation using a click formulation. So the click are pre-computed. And I set a timeout of 30 minutes. So for graph of 200 nodes, we observe that decision diagrams, so this method, this one, and this one, are generally speaking better than Cplex. The one that is able to close the search within the less node is our first method, based on reinforcement learning without improvement, but it is also quite slow compared to the mean heuristic. And the best one in determining execution time is the one using the improved version of the variable ordering. Now, if I increase the size of the DD, now Cplex is not able to prove the optimality and to obtain a gap of 0%. And the best one is still the one using the learned variable ordering. And if I increase still again the number of nodes, so now we can achieve an optimality gap of around 4.7%. And the second best method using mean state is around 7.2%. And we reach the timeout, so we are not able to prove the optimality. Okay, so the message here is that decision diagram can improve our Cplex, but that's something that was already known by Andre and David for the maximum embedded set. And what we show here is that we can use machine learning to close the search faster and reducing the optimality gap. So the research question that I wanted to address in this talk is, can we use efficiently machine learning to speed up branch and bond algorithm? And the answer is yes, in some case. And on this talk, I focus on learning optimization. Tight bonds are important in a search tree. And it is a topic that is almost not considered in the literature compared to learning to branch. So the contribution of this work is that we propose a generic framework to learn bond from a recursive formulation. So the framework is this one. And we have better performance than classical ordering for the maximum independence set. And we show some ability to beat Cplex for this problem. So that's the current result that we have, but we have a lot of future work. So if you are interested about it, feel free to ask me if you want some more results. So first of all, we want to investigate other options to reduce the execution time. For instance, it can be inside the neural network architecture. We can use kind of a network pruning or knowledge distillation. I know that Thiago is working about network pruning using integral programming methods. Also, we want to go beyond the maximum independence set. So it is the most successful case study In a paper that is currently submitted, we have results on the maximum cut, set covering, and knapsack. But so far, it is really on the maximum independent set that we have the best result and that we are able to beat integer programming model. Also, something interesting that we have already discussed with a question in the chat is we can consider directly the diagram as input of the network and not the instance. So if we are able to use the decision diagram as input of my neural network, or maybe a graph neural network, I can be generic to any case of problem. So far, we need to translate the input of the instance as input of the neural network. And again, maybe here it is one of a long-term research goal. We want to use this to provide a bounding mechanism to CP solver. At the moment, CP solvers are very good because we have high flexibility on the search, but we don't have a flexible and generic bounding mechanism. And I think decision diagram can play a role in that. And it can be also a bridge using machine learning inside the solver in order to learn how to bound. Okay, I arrived at the end of this talk, and I want to finish by many thanks to all the professors, students, and researchers that have collaborated in this work. So the work I presented here is 4 contributions here. So it is Louis-Martin Rousseau, my former supervisor for my postdoc. David Berman, who initiated the idea to use machine learning for the variable ordering. André Seri for the big picture about DP and try to combine everything for a solver using the reinforcement learning, decision diagram, constraint programming. Augustin, a PhD student I supervise, who has worked a lot on the integration of branch and bound. Isabeau, a researcher from company, who helped me a lot about the neural network architecture, and Emmanuel as an intern I have supervised. So thank you very much for your attention. And now, if you have a question, I think we have a few times now.
Yes, please. Quentin, I already have some questions for you. Ahmed, can you please comment on the generalizability of the RL approach, e.g. testing on graphs of different density and on real-world graphs?
Very good question. So generality is an issue with reinforcement learning. So we have, if we have instances that have the same distribution during the training and evaluation, we can have good result. But when we differ slightly the distribution, the results are not so good. We have studied this in the paper, and you will see that if we increase the number of nodes too much, the result won't be good. And it is the same when we increase or we reduce the density. So it is important to be able to encapsulate the distribution of the instance that you want to solve. One exception is using the width of the DD. We have observed that if you train on DD using a width of 2, you can still extend it to width of 10,000. So that might be the most surprising result that we have. And one intuition with that, it means that the variable ordering that is good for a DD of 2 is also good for a DD of 10,000. Do I answer your question? Okay, great, thank you. Other question?
Any more questions? All right, so let's thank Quentin. Thank you so much for the great talk. If you still have questions, feel free to reach out to Quentin. I believe he's going to stay with us for a little bit longer. And let's take a quick break. Thanks so much for the excellent talk, Quentin. And we come back at 11:15 for our next talk on column generation approaches based on DDs, I believe, by Willem. All right. See you later at 11:15. Please take this chance to drink some water, keep yourself hydrated, and see you soon.
Thank you very much. It was a pleasure to present my work, and thank you for your attention.